In 1930, deep within Tokyo Institute of Technology, two Japanese researchers mixed iron oxide with zinc and manganese, then fired the combination at extreme temperatures. What emerged was ferrite, a ceramic material with magnetic properties that defied conventional physics. A decade later, as World War II consumed the planet, this material became essential to radar systems, submarine communications, and encrypted radio networks that connected armies across continents. When the war ended, ferrite quietly disappeared into the circuits of everyday electronics. For 70 years it powered televisions, telephones, and computers, hidden inside transformers and inductors nobody thought twice about. Then scientists examining renewable energy storage rediscovered it. What they found changes everything we thought we knew about clean power transmission. This ceramic material, perfected through the demands of total war, might hold the key to solving our greatest energy challenge: how to store and move renewable power without losing half of it along the way. The story begins in pre-war Japan. Doctors Yogoro Kato and Takeshi Taki at Tokyo Institute of Technology were investigating magnetic materials when they synthesized the first ferrites in 1930. Their discovery emerged from pure research, an attempt to understand how different metal oxides behave when combined and heated. What they created possessed a strange duality. Unlike metals, ferrites are electrical insulators, yet their magnetic properties rival or even exceed those of iron. This paradox, well, it becomes their superpower. By 1937, TDK Corporation began mass-producing ferrites for military radios. As Japan prepared for war, the material's advantages became, really clear. Traditional iron cores in transformers and inductors worked for basic power transmission, but at radio frequencies, they failed catastrophic. Energy bled away as heat, systems overheated, equipment died, ferrites remained stable where metals collapsed. At high frequencies, metals generate destructive eddy currents that waste energy. Ferrites, being insulators, avoid this problem. They guide magnetic fields without bleeding power. During the war, the demand for advanced magnetic materials soared, as nations sought to improve communications and radar systems. Ferrites quickly became essential, not just for their magnetic properties, but also because they could be produced without using scarce metals. After the war, these discoveries paved the way for a whole range of new applications, from telecommunications to early computers, making ferrites a cornerstone of modern electronics. During World War II, multiple nations raced to perfect ferrite technology. While Japan led early development, researchers in the Netherlands at Philips made crucial advances between 1944 and 1945. J. L. Snook's work on soft ferrites created commercial formulations that would dominate post-war electronics. By combining iron oxide with other metallic elements like manganese, zinc, or nickel, then firing the mixture at temperatures exceeding 1,000 degrees Celsius, engineers created ceramics with astounding electromagnetic properties. The military applications spread fast. Radar systems that detected incoming bombers relied on ferrite cores. Submarine communication systems used ferrites to transmit signals underwater where conventional systems failed. The Germans, Japanese, Americans, and British all integrated ferrites into their most advanced electronic warfare equipment. After the war, the technology spread to consumer markets, finding homes in television sets, telephone systems, and early computers. For decades, ferrites powered the electronics revolution, hidden inside nearly every device with a transformer or inductor. Yet their application remained narrow, confined to small-scale electronics. Nobody imagined using them to revolutionize power grids. The renewable energy crisis, well, it forces us to think different. Solar panels and wind turbines generate clean electricity, but they suffer from a fundamental flaw: intermittency. The sun does not shine at night, wind does not blow on schedule. We need massive storage systems to capture excess energy during peak production and, release it during demand surges. Current solutions involve lithium batteries or pumped hydroelectric storage. Both have severe limitations. Batteries degrade, and they use rare earth minerals mined through destructive processes. Ferrite-based systems offer another path. Modern research into ferrite compounds reveals they can store electromagnetic energy in ways batteries cannot match. When paired with superconducting materials or advanced capacitor designs, ferrite cores can hold massive amounts of energy in magnetic fields. Unlike chemical batteries that degrade with each charge cycle, magnetic storage systems using ferrites show minimal wear. They can cycle thousands of times without performance loss. The transmission advantage becomes even more compelling. Power grids lose between 5 and 15% of generated electricity during transmission. Those losses occur because alternating current in copper wires generates heat and electromagnetic radiation. Ferrite-enhanced transformers and transmission systems can reduce these losses dramatically. By shaping and controlling magnetic fields with precision, ferrite components keep energy flowing where it belongs, through the system, not into the surrounding environment. Ferrite technology, honestly, is finding its way into an ever-growing range of applications. From telecommunications to electric vehicles and even renewable energy systems, ferrite materials are proving to be, incredibly versatile. As our demand for efficient energy transfer and minimal losses continues to rise, the future of ferrite technology looks both promising and essential. Researchers are exploring new formulations and innovative designs, aiming to push the boundaries of what's possible with ferrite components in the years ahead. Consider the application in offshore wind farms. These installations generate enormous power far from coastal cities where demand concentrates. Subsea cables stretching hundreds of miles must carry that energy to shore. Every mile increases loss. Ferrite core transformers at strategic points along these cables could step voltage up or down with unprecedented efficiency, maintaining power quality across vast distances. The same principle applies to solar farms in deserts, connecting remote generation to urban centers. Recent advances in ferrite synthesis have created materials far superior to what wartime engineers produced. Nanostructured ferrites, created through precision manufacturing, exhibit magnetic properties that seemed impossible decades ago. They operate at higher temperatures, handle greater power densities, and maintain stability across wider frequency ranges. Some formulations show magnetic permeability thousands of times greater than iron, meaning they can store and direct magnetic fields with extraordinary efficiency in compact spaces. The energy storage systems under development now resemble nothing from conventional power engineering. Imagine, if you will, warehouse-sized installations where ferrite cores the size of trucks sit at the heart of superconducting magnetic energy storage rings. During peak solar production at midday, excess electricity flows into these systems, creating powerful magnetic fields trapped within the ferrite matrix. At night, when demand rises and solar panels go dark, those fields collapse in controlled fashion, releasing the stored energy back to the grid. The cycle repeats endlessly without the chemical degradation that limits battery systems. Challenges remain. Ferrites require rare earth elements in their optimal formulations. Mining these materials carries environmental costs. Manufacturing ferrite ceramics demands high-temperature kilns and precise chemical control, making production energy-intensive. Scaling from electronics applications to grid-scale infrastructure requires massive investment in new factories and supply chains. Yet these barriers appear surmountable compared to alternatives. Ferrite production does not require the toxic chemical processes that plague battery manufacturing. The materials themselves are stable, non-flammable, and recyclable. Research institutions across Japan, Germany, and the United States are racing to scale ferrite technology for grid applications. Prototypes demonstrate the principle works. Test facilities in Japan use ferrite core transformers to connect offshore wind turbines to the mainland grid, with 12% less transmission loss than conventional systems. Pilot projects in Germany store solar energy in magnetic fields held by ferrite matrices, releasing it during evening demand peaks with 95% efficiency. Over the decades, the journey of ferrite technology has been marked by persistent innovation and, honestly, a fair bit of trial and error. From its early days as a laboratory curiosity to its current role at the forefront of energy transformation, ferrite has come a remarkably long way. Looking ahead, researchers are optimistic that continued advances will unlock even greater efficiencies, making renewable energy more reliable and accessible for communities worldwide. The future, it seems, is being shaped by the quiet power of ferrite. What makes this story remarkable is not just the technology, but, the circularity of innovation. A material developed in 1930s Japan, perfected under the extreme pressure of wartime necessity, designed to solve communication problems during World War II, now offers solutions to the defining challenge of the 21st century. The engineers who first synthesized ferrites could not have imagined their creation powering a carbon-free future. They were solving immediate problems, not planning for renewable energy grids. This pattern repeats throughout history. Technologies developed for one purpose often find their greatest application elsewhere. The Internet began as a military communication network. GPS started as a missile guidance system. Microwave ovens emerged from radar research. Now ferrites, born from pre-war research and perfected in the crucible of total war, might become the foundation of sustainable energy systems that power human civilization for centuries. Stand at the edge of this transformation and look both backward and forward. Behind us, the laboratory benches of 1930s Tokyo, where patient researchers created something remarkable. Beyond that, the smoking ruins of 1940s warfare, where desperate engineers perfected it. Ahead, cities powered by wind and sun. their energy stored and transmitted through materials those researchers would recognize. Between then and now, 90 years of quiet industrial application, ferrets working in anonymity inside every electronic device, waiting for someone to recognize their larger purpose. The energy revolution we need has been hiding in plain sight, waiting in a discovery made nearly a century ago, ready to be rediscovered and reimagined. Sometimes the future is not about inventing something new. Sometimes it is about seeing what was always there, understanding it different, and having the courage to build something magnificent from the foundations of the past. Subscribe to Through Time to explore more forgotten technologies and hidden histories that shape our future. Share this story with anyone who believes innovation is not just about moving forward, but about knowing where to look back